This is the sixth and second to last lesson for Unit 6 for our AP Calculus, and we're going to be looking at, it's a pretty long lesson here, looking at exponential growth and decay. The two ideas are actually very much related together, and we're going to start off on this page just by kind of looking at, what is this exponential growth, how is it defined, how do you know that it's happening? And then on the next page, we'll look at how do you solve the differential equation for it, and then we're just going to try a few little stories out, a few examples. But on this page, let's talk about what exponential growth actually is. And I'm going to throw some color at this, and over here I'm going to put some, throw some English down, use some words, and then we'll convert that phrasing into a nice differential equation. So you've got exponential decay when a population, okay, I'm going to switch up colors here on you, grows at a rate. Okay, new color. We'll see how this all fits into the differential equation. That is proportional to another color. Its own size. So in other words, the bigger the population, the faster it grows. Now, how do you write that as a differential equation? Well, I'm going to pick up on that red word there, rate. That's how fast your population is growing. I can use any letter I want for the population. I could use P, I could use Y, I could use X, whatever I want. I'm going to go with Y, and I'm going to say, okay, that's when dy dt, there's my rate of growth, right, as time goes by. It's supposed to be proportional to, well, I know how that works. That means you go is equal to k times. Okay, well, what is it proportional to? Well, it's proportional to its own size. Okay, so that's the story where the derivative of its growth, right, its fraction there, that Leibniz notation for the rate, is equal to some constant multiplied by how much you've actually got there already. A good example of exponential growth might be bacteria, and another good one is rabbits. So let's say that y, which is a function of time, depends on the time of day or the time of year, is actually going to be the population of rabbits at time t. The units for that? Well, it will be measured in rabbits. The derivative, y prime, that dy dt, this is going to talk about how fast your population of rabbits are growing. So this is going to be the growth rate. And that would be measured in rabbits per some sort of time. I'm going to go rabbits per year. And so the whole idea of exponential growth is that if you've got a bigger population of rabbits on your rabbit farm, then you're going to have a bigger growth rate, a larger value of rabbits per year of growth. Just throwing some random numbers out there. Let's say you have a little rabbit farm and you have 8 rabbits on your farm. Then rabbits doing what they do, you might find that you've actually got new rabbits when you go and check on them, and maybe the growth rate, maybe the rate at which the population is growing might be 12 new rabbits per year if you have 8 rabbits in your little rabbit farm. But if you had a bigger rabbit farm, if you went big and had a farm of 80 rabbits, well, it's all proportional, right? So if you've got 10 times the population, then you should expect on a rabbit farm full of 80 rabbits that you would have 120 new rabbits per year. That's all exponential growth is about. Just saying that the growth is proportional to how many rabbits are already there. So we've got our differential equation, right, where the growth rate is proportional to the actual population. So y prime is equal to k times y. In this format, when we have that k in there, that constant of proportionality, this particular constant of proportionality is usually called the growth constant. But thinking back to just when we were doing proportionality questions in general, I mean, yeah, it is the proportionality constant. So maybe I'll put in here, or proportionality. constant. Usually we would just call it the growth constant. Now, for our rabbits, looking at just this story where if there are 8 rabbits, then they're growing at 12 per year, or if there's 80, they're growing at 120 per year. In my little made-up example that you see up there, it looks like in order for me to figure out what that rate is, how do you get 12 from 8? By multiplying by some sort of k, right? So I'm just kind of staring at it going, hey, well, I seem to be getting 12 when this number here was 8. Looks like in my story, the growth constant here is 1.5. So y prime is equal to 1.5 multiplied by y. Or if you want the Leibniz notation, dy dt is equal to 1.5 multiplied by the y. Now in this lesson we're mostly going to do exponential growth, but we'll do exponential decay as well. And what you'll find is you're losing stuff if it's exponential decay, and so the k will actually be a negative value. So if k is positive, it's going to be growing, and if k is negative, then your population is going to be decaying. It'll be diminishing over time. So that's the story for what exponential growth is. Now let's look at how you actually solve that differential equation. Okay, how does this actually work? I'm going to just split this page here so I've got a little bit more room, and I'm going to see if I can solve this differential equation. Well, as I look at it, it's separable. It's got y's over here. It doesn't even have any t's at all, but it does have y's over on the right-hand side. So I don't want them to stay there. I'm going to have to move them. So I'm going to write this, if I divide by y, as 1 over y times dy is equal to, I'll leave the k there, it's just a constant, and then I'll bring the dt up to the other side. So there, I've separated the variables, and now I'm going to go and drop in an integral sign on both sides. We're going to integrate. Now that story on the left, I've seen that before. When you're integrating, just 1 over the variable, often we're using x's, we're integrating 1 over x, and we'd be like, oh yeah, that's ln x, right? Well, here it's y's, so this is going to be ln y. So I've got ln of y. Now you should, I guess, technically put absolute values on this, but don't worry, y is actually keeping track of how many rabbits are in your population, and it's not going to be negative. So we don't have to worry about that issue at all. We're going to take those off pretty quick. Now over here, k isn't the variable. K is just a constant. T is the variable. So this is actually going to be k times t, the constant multiplied by t, plus some sort of constant that we pick up. Okay, so far so good, but I don't need to have those absolute values there. Okay, they're quite optional. So let's get rid of them because our population is definitely positive. So I've got ln of y is equal to kt plus some sort of constant. I want to know what y is, not what the ln of y is. And we've seen this before, just on the previous page, where if you want to get to y at this point, you can exponentiate both sides. And then you would have on the left side just a straight up y. But then as you exponentiate the right side, you would have equals that constant times t plus this c, this arbitrary constant that we're using just to make sure everything is going to work out very nice. Now, we often don't like to write it that way. It doesn't work out well to try to find a c up in that exponent position. It's just remarkably awkward to have it up here. So I'm going to move it. I'm going to do a little algebra manipulation here. And I'm going to say, hey, this is the same thing as a multiplication story that was e to the c multiplied by e to the kt. Because if you were multiplying those powers with the same base, you would add the exponents up. You might say c plus kt, and I've spun it around backwards because what I'm going to do is modify this and say, hey, e to the c, that's just some other constant. This was a game we played, I think, on the previous page, a couple of pages back. We said, well, instead of calling it that, trying to find some awkward number up there, why don't we just call it a different constant out front? Now, if it bothers you that I'm saying, oh, well, e to the c is just equal to c, if you really want to, you could go and put some subscripts in here, and you could say, well, there was a constant here, we'll call it constant 1, and this is a different constant here, constant 2. But most math people don't even care about that, right? They're saying, well, the c is there just to keep it general, and they would actually use that little phrase without loss of generality, saying, yeah, no big deal. Let's go with a c out front. It's actually really, really nice. Now, in a couple of seconds, I'll show you how to find the c. It's remarkably easy. But first, let's just do a quick little check of this general solution. Right? So we've found the general solution, y at any time t is equal to some constant e to the kt. Right? That's our general answer. It'll only get specific once we throw in some nice value for that c. But let's just check this out and make sure it's okay. So I'm just going to do a quick little derivative here to make sure it's happy with the differential equation. What would dy dt actually look like? What would y prime actually look like here? Well, it's a nice little exponential with a c hanging around out front. So that c is going to stay there, constant multiple rule. Hey, it's an exponential, so that's just going to look the same. That would be e to the kt. And then the chain rule would kick out a k when I go to do the derivative. And if I just rewrite that with the k on the front end of it, I could say, well, that's k times c e to the kt. And here's the beautiful magic that just happened. We have actually got right back to where we were. This is actually just y. And so we've actually created this situation where after doing a derivative, this y prime that we had right over here, the derivative of y, it turns out is actually just equal to k multiplied by y. It has done exactly what we wanted it to do. It is perfectly doing this differential equation we have up here at the top of the page, okay, where we said, all right, if you take a derivative, it should be just like the original thing, but maybe multiplied by a k. And that's exactly what this general solution is doing. So everything is perfect. I like it. Now, how do you go and find that capital C in your story that you're working on? Well, we actually use the initial conditions in order to find it. So this is just going to be the value for y, the value for your rabbit population when t is equal to 0. Okay, so what if somebody said to you, yeah, I've got this population of rabbits. I had 8 of them, and then there were 12, and the next year, and they were growing at 12. And you're like, okay, great. I think I know what the k is. It's 1.5. And then they were say to you, I started off with 4 rabbits at time 0. That's actually a neat way to figure out what that value for capital C is. So I'm just going to split this page here a little bit. Let's take our story in general. So our general solution said rabbits at any time t will equal some c that we're trying to figure out, like, what is it doing? And then e to the k times t. And in our made-up story, the k was 1.5. Well, if I go and put in a time of 0, think about what's going to happen to your math here. If you said, well, how does this math work out when I put 0 in for time? I would have c and then e to the k, which I think in our story was 1.5, but multiplied by 0. Well, k times 0 is just 0, so I would have c e to the 0. But e to the 0 is just 1, so I would have c. So it looks like, and it turns out it perfectly is, that this capital C is actually just your original number of rabbits. Okay, so that's a remarkably important thing to note, that C is the initial value, the t equals 0 value for y. So for our little made-up rabbit story, let's grab a color here. Let's go with this one. If you start off with 4 of them, and if they were growing at that rate where on the previous page we said, well, you know, if you have 8 of them, you're going to have 12 grow, 12 new ones every year. So the k would have been 1.5 in that story. Then for our rabbits, you can say, oh, here is a little predictor for how many rabbits you're going to have at any time. It would be 4 and then e to the 1.5 t. And that population is going to explode. That's how exponential growth works. If I go to my calculator and say, okay, calculator, let's try this out here. Let's see what you got. 4 e to the 1.5. I don't have t's, but I can go times x. And I'm going to see what this population does. So I'm going to start off just with, I don't know, zoom 6. And we'll see. So really focusing on what happens after time 0. And this population is just going really quickly up. So I'm going to change my window here so I can see better. I don't need negative time. Let's go forward maybe 10 years. And I'm going to have to set my maximum to something ridiculous. Like, I don't know, I'm going to go 10,000 rabbits. And maybe tick marks every 1,000 rabbits. All right, so here's your population. It starts at 4, and then it just goes through the roof. That is exponential growth. Because the more you have, the quicker it's growing. And so this starts way down here at 4, and then just grows like crazy. Okay, if you want to see that original 4 value, you'd have to get a little closer here. Let's only go for 2 years. Maybe we'll go from -2 up to, I don't know, 8 tick marks every rabbit. So here we are starting at 4. Oh, even that, it's just so quickly escalating, not even going high enough here. Just do one more of these. Okay, starting at 4 and then through the roof. Okay, classic exponential growth. All right, so on the next page, this really is just an aside. Do not sweat the math you see on this page because I just want to show you a comparison from the way you might have done this in Math 12 and also the way your TI-83 or 4 wants to do this, and then the way we like to do it in Calculus. So let's say you've got some rabbits and your math teacher tells you that you start with 50 and they're going to double every 6 months. And they want you to come up with some way to keep track of your rabbits. And so, I don't know, maybe you don't like using R, or Y, maybe you want to use R. So I'll have R of T be my number of rabbits. What you might have done in Math 12, when you were just kind of learning about writing exponentials, you might have said, hey, this is a great way to figure out how many rabbits there are later on. We're going to start off with 50, because they said so right here. And then we have to double the population every time 6 months go by. So what you could do is you could put in a little doubler here, a little 2, that will double the population. And the question is, well, how many of those 2's do you need? Well, every time 6 months goes by, you need to throw one of those 2's at it. So if it's 12 months, throw a couple of 2's at it. If it's 18 months, throw 3 2's at it. And so in Math 12, you probably would have done something like this. T divided by 6. That could have been your exponent up there. And so if you measure your time up here in months, then that fraction T over 6 figures out how many doublings would occur. And that feels good, right? You look at it and go, yeah, that makes sense to me, right? That you would use a 2 because the population is doubling, and that little 2 is going to do that doubling for you. But if somebody asks you, well, how quickly is your rabbit farm population growing 15 months from now? The answer is, I have no idea. So Calculus does a much better story on that. The Calculus just works better. Instead of using a 2 down there for that exponential base, we're going to use an e. Now that does mean that the exponent's going to look a little bit strange when we go and put our k up there. But here's what we would do in Calculus 12. We would say, okay, let's rewrite this. Let's say that our population of rabbits at time t is equal to 50 rabbits, right? That would be the units. I'm even going to put the units in here. Now, don't sweat the math here too much, right? I'm just going to show you kind of our general plan. And after you've done this a number of times, it'll feel a little bit more comfortable. I don't want to use a 2. I want to use an e. And then I'm going to go to the kt, and I'm going to put a constant up here. And the way that you find the constant is you say, well, if my general story, just in general, I'm just going to go over here, go for a little aside for a moment, and say, all right, if generally my number of rabbits is equal to, some constant, e to the kt, and that constant is my 50, my original number, well, I'm going to get to the point where I have double that. I'm going to have 100 rabbits if I start with 50. When I have e to the k times, hey, they said so, 6 months. Okay, well, I could divide by 50. 2 would equal e to the k times 6. So if I want to solve for k, I'm going to have to take the ln of both sides. And I could say, all right, ln 2 is equal to k times 6. And if I want to know what the k is, I'd have to take ln 2 and divide by the 6 months. Okay, so I can do that. Say, okay, ln of 2 divided by 6. Some weird number. Doesn't feel right, but it's going to work really well. 0.1155. The units are really strange because this 6 right here, this is 6 months. So the k is actually ln 2, which has no units, divided by months. And so up here in the exponent, we would say, oh yeah, here's a great exponent. It's going to work really, really well. 0.1155. And the units they're weird. They're upside down months. It's like divide by months. So a lot of people just go months to the -1. That's my k, and then they put a t there. This will work super well. And you might think, no, I like the Math 12 one better. Well, it's going to work really well when people ask you, well, how fast is the population growing at 15 months? You know, what's that derivative of r at 15? No problem. If you're telling me that that r is 50 e to the kt, then what I know is I can easily find r prime. I'll just take a derivative of that, and it's going to look exactly like it, but it's going to pick up a k. So it's going to be that same awkward k, and then the 50 e to the kt. So I could easily tell you what your growth rate of rabbits would be. I would just go, okay, 0.1155, and those units are upside down months. And then I would right here figure out how many rabbits are there at that moment. So e to the 0.1155. And oh, you want to check at 15? No problem. Now, when you first figure out just this part here figures out how many rabbits you've got. That's the number of rabbits at 15 months. But then when you multiply by k, all of a sudden that r value, right, so this is just an r, suddenly that r value when you multiply by the k turns into an r prime. And so that's all you have to do to find out the rate of change of rabbits is just take your rabbits and multiply by the k. And it'll tell you exactly what your growth rate of rabbits are. And we'll do some of those on the next question, the next page. Your TI-83 does something totally different. And it feels that it can do this to calculate answers quickly. So if you ask it to fit some data that's all exponential growth, it actually does kind of an odd thing. It says, okay, well, you had in your Math 12 story, r is equal to, your rabbits were equal to 50, and then you had this doubler in there, 2, and then t divided by 6. That was kind of the Math 12 way of looking at it. And your TI-83, when it fits the data, if you ask it to, it would say, well, that's kind of like 50. And then you could say it's a 2. And then you could write this as 1/6 times t. And then your TI-83 goes a step further and says, well, that's like 50 multiplied by a 2 to the 1/6 all to the t. That's just the rule for stacked up exponents that you'd multiply. So your TI-83, if you ever ask it to fit data, it would actually go, oh yeah, here's the answer. Here's the nice equation, 50. And then this really weird looking base, it just seems to come out of nowhere, 1.1224, but then it just has to put a t on it. It doesn't have to have a k up there. And it thinks that that looks really nice. So if you ever do ask your graphing calculator to fit data, it'll do that. We haven't done that very much this year anyways, but if you do ask it to do that, it'll make it look like that. Don't worry about this page. Okay, so this whole page here, just showing you different ways of basically saying the same thing. You know, there's what you learned in Math 12, there's this way, that's great. And then there's this way that we're going to use for calculus. It'll work really well. And the TI-83, yeah, it does something even different again. It says, oh, I want to talk about the rabbits this way. We're going to go with that middle option. It'll be super nice for finding rates of change. So let's try a question out here and see how it goes. So this example 2, what do we got here? Oops, that was kind of bad. Let me kick that down here a little bit. Okay. There we go. Got the pages sorted out here now. Example 2. A population of bacteria grows at a rate that's proportional to its own size. Okay, that sounds like exponential growth to me. The bacteria culture starts off with 800 bacteria, 5 hours later up to 12,000, and the first thing we're going to do is find the amount at time t. We can use any letter we want. We could go B for bacteria. We could go with Y, whatever we like. Okay, I'll go with Y. Now, pretty quickly, you'll just jump right to the answer, but let's take our time on this one. We've got a whole page to write this out. The differential equation is this. dy dt is equal to k times y. That's the story for exponential growth. Okay, the solution. What's it look like when you get to the answer? Well, you would do separation of variables. Right? You would say, oh, okay, I'm going to write this as 1 over y times dy is equal to k times dt, and we just integrate. And when you do that, the solution ends up being y of t, your bacteria count. It's actually going to be some constant, which is just the initial amount, and then e to the kt. Lots of times scientists, because this is just going to be the initial amount, they just call that y with a little 0 subscript on it. So they'll say, okay, your population generally is y naught, okay, just the initial population, and then e to the kt. So that's just a way of saying the initial value, right? That's all that y naught means. Okay, so it looks like for our story here, they've told us that we're going to start with 800 bacteria. So you could say, oh, okay, my bacteria at any time, it's actually just equal to 800 e to the kt. Right? That'll be a beautiful little way of knowing how many bacteria there are. The only thing that I don't know right now is, wow, what's that growth constant, right? What's the k that's going to go there? So let's go and see if we can find that. And I know I did it really quickly on the last page. I'm going to slow it down here now. So let's go after that k. They had another little bit of information there. They said after 5 hours, we're up to 12,000 bacteria. Well, let's put that information in, right? Let's say, okay, if I go y figured out at 5, right? I'm just going to put that 5 in for t. Then that would be 800. I'm going to put units in here eventually. Okay, in fact, tell you what, let's get this right now. There's no reason why we can't do it perfectly right off the start. I'm going to put 5 in, and it's 800, the initial amount. The units for that are bacteria. And then that gets multiplied by e to some k that we're trying to figure out, and then it's kt, right? Well, this is at 5 hours. Okay, well, let's put that in. We've got 5, and I'll throw the units in here too, hours. That needs to work out to be, because they said so, 12,000 bacteria. All we're going to do is a little quest here, a little journey to find out what k is. Just using a little math 12. You could divide 12,000 by 800. In fact, I think that goes pretty nicely. Divided by the 800, so 12,000 bacteria divided by 800 bacteria. I'm dividing bacteria by bacteria, so there will be no units left when I'm done, and I'll be staring at this equation. E to the k times 5 hours is equal to just a straight up 15. It was bacteria divided by bacteria, so you don't see anything anymore. I'm now going to go and take the ln of both sides. So if I ln both sides, I'm going to have k multiplied by 5 hours is equal to the ln of 15. Okay, I think I'm there. This k, I can give it to you in exact form, and then I'll give it to you as a decimal. In exact form, it's the ln of 15 divided by 5 hours. In a decimal form, if that feels a little bit better, let's see what we have here. Ln of 15 divided by 5. 0.5416. Okay, so we're around 0.5416, and the units are divide by hours, often just written this way. Okay, I'm ready. I'm ready to write down my final answer. My machine that will describe this exponential growth, the amount of bacteria at any time people want to check, it's equal to 800, and the units there are bacteria. You don't have to put the units in, but they're kind of helpful to see. And then e to the 0.5416 upside down hours. There's your K, but it's multiplied by T. So as long as you throw T's in there that are in hours, then the hours and upside down hours will cancel, and then we can figure out how many bacteria we've got. And that's exactly what we're going to do on the next page. Okay, so the next page here says, great, now that you've got that machine working super well, how many are around after 2 hours? So this is what it would look like to go and use that machine now. You'd say, oh, okay, well, let's just go and sub in 2 hours. So Y, the bacteria count at 2 hours, it would be 800. And again, you don't always put the units in all the way through, but I'm just doing that here just so you can see how well this actually works. 800 bacteria multiplied by this exponential, 0.5416 upside down hours, that's the K. It has units of upside down time, and then I'm going to multiply it by 2 hours. And so the word hours cancels, right? You've got hours and upside down hours, that's gone. And all you have to do is take 0.5416, multiply it by 2, and then you go e to that. And then finally you multiply by 800. And the answer for how many bacteria there are 2 hours later, it's around 2,363. Now, when you're doing these population stories, you could go 4 decimal places if you want and say, hey, it's a rounding, you know, bacteria are growing, they're splitting. Or you could round to the nearest bacteria. Either makes sense, nobody cares. It's all good. Now, this question right here is super important. And it's actually, when you do it the calculus way, pretty darn easy. They want to know the growth rate right at that 2 hour mark. So they're now asking us, if you were to look at that bacteria and just kind of look at the little petri dish of them growing and splitting, and if you were to do it right at the 2 hour mark and look at it in like an instantaneous sense, what we want to know is right then, what is our observation for the bacteria per hour of growth? How many new bacteria are being added every hour? It's really, really, really nice to do this using the calculus because we had this differential equation that said, oh, y prime, which is this derivative we're after, it's actually just equal to k times y. In other words, it's just equal to that growth constant, which we already know, multiplied by the population size. So if we want to know what the growth rate is right at time 2, it's actually pretty easy. We're just going to take our k value, which was 0.5416. Remember, it had units that were upside down hours. And we're going to multiply it by how many bacteria are present. And at that moment of the day, it's 2,363. You know, if you wait longer, there will be more bacteria, and then this growth rate will be higher. So all you need to do if you want to find rates of growth, that rate of change, all you have to do is take the population and just multiply by the k. Okay, that's all that's happening here. This is just nothing more than k times the current population. And what you find when you actually check this out for this story is at time 2, when there are those 2,363 bacteria there, this thing's growing at around 1,280. Looking at the red units there, the units are actually going to be bacteria per hour. So this is the absolute beauty of using this method. It is so seamless to transition between y's and y primes, or back again, right? You can talk about the amount of bacteria or the growth rate. Okay, part D, just a little Math 12 question. There's really no calculus here at all. It says, hey, would you be able to figure out when in the day there are 18,000 bacteria? And I would say, yeah, sure, we can do that. We've got this machine that tells you the bacteria at any time. It's equal to 800. And then E, we had that K up there, right? So the K was 0.5416. Or you could write that if you want in nice exact form. What was it, ln of 15 over 5 or something like that? Multiplied by some t. We're looking for this t. We don't know what it is, right? It's like, go find the t. We need that to hit 18,000. Well, I would divide the 18,000 by 800 right away. That's got to be your first move. Okay, 22.5. All right. So it looks like E to this K value that's just not going to change all day, not for these bacteria, to the T is equal to, what was that number again? 22.5. And now you can go and take the ln of both sides. So you're going to have, once you ln this, 0.5416 T is equal to the ln of 22.5. Okay, we're there. The time when this is going to happen, it'll be one brief instant. It's actually going to be the ln of 22.5. And then you'll have to divide by this K. Now remember, the units for K were actually upside down time, but you're dividing by it, so we're actually going to get back to the hours, which will be awesome. So 0.5416, the units here, those were hours upside down. Well, that'll actually give us hours in our answer. And so this works out to be around 5.7486 hours. So far, so good. The next story here has very, very little to do with calculus, and it's really just more of a Math 12 question, just looking at how to use some logarithms creatively. The trouble here is they don't tell you how many bacteria there are right at the very, very beginning. Instead, they tell you that, oh, geez, we waited 4 hours to check, then there were 500. So there would have been less than that at the beginning. And then, oh, they're up to 1,500 at the 12-hour mark. And you have to see if you can figure out what the actual population is at any time t. It's doable. It's totally doable. Here's the way I would go at it. I know that generally the solution looks like this. The amount of bacteria at any time, it's equal to the starting amount, but I don't know what that is. That's a mystery. And then e to the kt. Right, so that's the general story. But what's missing for me right now, some values that I just don't know. I don't know what the original amount is, and I don't know what the growth rate is. I do have a couple of clues, though. Okay, they've given me some little conditions that I can throw at this to see if I can use them to solve this story. I know I'm supposed to hit 500 when the time is 4. So let's look at that blue equation and just see, well, what would happen, right? How would that look when you're going to go and put in a time of 4 and you have to get 500 out of the story? That's not too bad, right? We could say, okay, why not? We don't know what that is, the original amount. And then e to the k, we don't know what that is either. Multiplied by 4 for time, that needs to be 500. And here's another story. The original amount multiplied by e to the k times 12, that's got to be 1500. Okay, so we got two equations there. We should be able to find these two unknowns. That's going to be our plan. It'll take us about the page to do it, but we should be able to get there. So I just wanted to put this on here to show you kind of a classic little way of solving this story, because these exponential growth questions are pretty darn common, and this scenario is pretty common too. And you actually do it by dividing one equation by the other. And I'm going to put the bigger one on top of the smaller one. So I'm going to say, what happens if I stack these? And I put y, e to the, if it's okay with you, instead of calling that k times 12, it feels better to say 12k. That's equal to 1500. And I'm going to take this story and I'm going to divide it by the other equation. And say, okay, what happens if I put the other one underneath it? Now, instead of k times 4, 4k just sounds better. And that was 500. Well, by doing that, I don't have to stare at two unknowns in this problem. I don't have to have y naughts and k's staring at me because the y naughts cancel. And I'll end up with just this division with the exponentials and then a nice little number over on that right-hand side. In fact, as I do this, right, if I've got e to the 12k divided by e to the 4k, I can actually just subtract exponents, right? That would be e to the 12k minus 4k, okay, otherwise known as e to the 8k is equal to, that would just be 3. Okay, well this is going to solve pretty quick. I can find k just by using logarithms. So if I do a log of both sides, I would have 8k is equal to the ln of 3. Right? That's what logarithms are for. So it looks like the k value is equal to ln of 3 all divided by 8 hours. Now again, you don't have to put the units in, but the 8 did have units to it, and it was hours. And if you want to write that as a rough decimal to 4 decimal places, that's 0.1373 upside down hours. We are close. We're close. We're halfway. Actually, a little more than halfway in terms of the effort. We've figured out what the k is. Now we're going to go and find out what the original amount is. You can pick either one of those conditions. You can pick either the 500 story or the 1500 story. It makes no difference. I'm going to go with the 500 story and say, okay, I got to get 500 when I go and put 4 in for time. So now I would have this. I would have y naught, which I don't know, it's still missing to me, and then e to that k, which I've just found, 0.1373. Those units were upside down hours, and then I multiply that by 4 hours. That needs to be 500. Well, this is totally solvable right now, right? I can just go e to that. I can get that value, divide, and in one move, I'm there. It's really not going to take very long at all. And I can find that the original number of bacteria, if I round to the nearest bacteria, is 289 bacteria. So all I would be doing there, I just say, okay, solving for this original amount, 500 divided by this exponential. Up in the exponent, I've got, these are rough numbers, it'll be close, 73 times a 4, and there's your 289 bacteria. So final deal, I've done it, I found those two missing things. It looks like the amount of bacteria at any time is 289. We always see the original number sitting out front, the amount at time 0, and then e to the 0.1373 multiplied by t. That'll tell you how many bacteria there are. And if you want to know how quickly they're growing, just multiply that by k and you're there. And that takes us to the last couple of pages where we're just going to spin everything around and say, what if it's not a growing population of bacteria or rabbits? What if it's actually getting smaller, like radioactivity in physics? So it's basically the same plan. It's exponential decay now for its name. And when does this happen? Well, this would be when a population, okay, some sort of total for how much we've got, when a population decays. So it's not growing, it's going to go away at a rate that's proportional to its own size. The differential equation looks exactly like it did before. Exactly. It's going to say, okay, the rate of population change is going to equal some constant multiplied by, that's how we do proportionality. And what is it proportional to? Its own size. And you're going to find out that there's a negative in this story. Some people overtly add the negative. Other people say, whatever, it'll show up in the K, but we're going to see that there is a negative, a single negative happening right there. A great example would be radioactivity in physics. So I might want to let Y, or any letter of my choice, be the amount of material at time t. You could measure that in any units you want, depending on how much stuff you've got. It could be grams, kilograms, buckets, whatever you want, right? I'm going to go grams. Whatever you like. And then Y prime would be talking about how fast it's going away. So instead of being a growth rate, if it's a radioactivity story, this would be the decay rate. And it's going to vary with time. And it would have units that feel kind of like this, maybe grams, and then divided by, whatever, hours, seconds, days, let's go seconds. The whole idea of exponential decay is the more radioactive material you have, the faster it's actually decaying away. Now, it doesn't vanish. A lot of people go, oh, yeah, it just disappears. It transmutes into some other material, but it certainly won't be present in its original form anymore. And if you were to have 400 grams of this radioactive oxygen-15, then what you'd find is it's actually leaving, it's disappearing, converting to, I shouldn't say disappearing, it's transmuting into a different element at a rate of negative 2.4 grams per second. In other words, every second off the start, you'd be losing 2.4 grams of oxygen-15 and then getting something else. But if you were to say, well, what if I had more of the stuff? What if I had 800 grams? Well, it's all proportional, right? So if with 400 you lose 2.4 per second, with 800, double the amount, you would have double the loss. That's what exponential decay and exponential growth are all about. The differential equation, it's the same thing, right? It's the same thing, but now instead of calling it the growth constant, we'll probably call it a decay constant, and there's going to be a negative sign in there. So when we go and solve the story, yep, it'll definitely be decaying away if it's negative. Okay, well, let's try this out with one last page right here. Some iodine-131, that stuff's radioactive. It's radioactive and it decays away with a half-life of 8.04 days. So if you wait those 8 days, you'll notice that half of whatever you had has converted, transmuted into something else, and is no longer iodine-131. Let's say you start off with 24 grams of the stuff. See if we can find the K in this story. Right? I'm going to just split my page here so I've got a little bit more real estate. Here's the kind of thing that I would do. I would say, well, the general solution is going to look just like it did for exponential growth. It really does look the same way. It's the same differential equation, y prime is equal to k times y. And it's the same solution, which is that the y later on, it's equal to the y at the beginning, and then e to the kt. And yes, we're going to find that there's going to be a negative in here. Some people put the negative overtly out front, and then their k is positive. We're going to just go and see that the k is negative. So there's a half-life to this story. We're going to be down by half after those 8 days. So let's kind of put in what we know, right? We start off with 24, that's this why not, but we'd be down to half. We'd be down to 12 if we started with 24, and then e to the k times, they said, this 8 days, this half-life, right? 8.04 days. Sometimes people, when they're talking about this, they'll kind of give this a fancy name. They'll say, oh, that's t1/2, right? Time for half of it to go away. Well, I could go and divide by 24, and I end up with this 1/2. So instead of rabbits that are doubling, I've got iodine 131 that's halving. And then over here, if the 24 is divided out, I'll have e to that k multiplied by that 8.04. This would have worked just as well with 120 grams after you started off with 240, right? As long as you have half as much here, you're going to find you always get a 1/2 there. And now as we continue to solve, we're going to end up with ln of 1/2 is equal to just the k multiplied by this half-life, this 8.04 days, right? So that half-life would just always show up right there. And so the k, when you go to look for it in these stories, it's going to be the ln of 1/2, which, by the way, is going to bring in your negative sign right there, all divided by your half-life time. For our story, 8.04 days. All right, let's just go and see what that looks like. The ln of the half, there's going to be your introduction of the minus sign, divided by the 8.04. Okay, the k for this story, I told you there'd be a negative sign in there. Yeah, it's negative 0.0862. And for this story with iodine 131, the units would be upside down days. Okay, great. So far, so good. They said, well, could you come up with just a general story for what the amount looks like? You betcha. Easy, actually. The amount of iodine 131 at any time, it's the starting amount. That why not always sits out front. So in this story, apparently, we're told we're starting off with 24 grams of the stuff. And then there would be that exponential e to that kt, so we would have negative 0.0862 upside down days, and then a t. There's your general solution. That would tell you exactly how much you've got at any time. You want to know, well, how much would there be at, I don't know, 20 days? Just go ahead and put 20 in for t, and it'll tell you the amount. Last question here. Find the decay rate after 12 days. This again is the part where calculus really, really, really excels. We've got y equaling the amount, and we have y prime is equal to the rate, which is what they're asking me about, right? What's the speed that it's moving around? And here is the absolutely beautiful thing. We know that y prime is just equal to k times y. So all we have to do to figure out what that y prime is, we just need to know how much there is at 12 days, and then we can multiply by the k. So I'm going to go and do that. Now, some people do that all in one step, and that is fantastic. I'm going to do it in 2 steps. Okay, just to sort of show you the idea. So let's go and find y. Let's go and find the amount. Okay, that's sitting there at that 12-day mark. So I'd go, okay, here we go. It's going to put 12 in for time. So y at 12, that would be my 24 grams, and then e, got my k for this story, multiplied by 12 days. Now the units, they work out beautifully. The k was kind of weird. It was days to the -1. The 12 is days, and those cancel. And so you just multiply those 2 numbers together, you go e to that value, then you multiply by 24, and what you find is the amount of material that's present still, that's still iodine-131 at the 12-day mark. We're down to 8.5292 grams. So we've gone and put in this time here of 12. Sorry, getting ahead of myself. This is the time, and that's the amount now that we've got. That many grams. But that's not what they wanted to know. They wanted to know, well, what's the grams per second? How fast is it leaving? This is the part that is so nice. Okay, so let's go for the rate. You want to get to the rate? Really easy. We're just going to say the rate, y prime, it's just equal to k times the amount. So all we have to do to find the actual decay rate at time 12, we're just going to take our k value, -0.0862, and we're going to multiply it by how much we've got, 8.5292. That's it. The units here are going to be awesome because this will be upside down days, and this will be grams. And then when you multiply those out, that rate at 12 days, at that mark, it's diminishing. We're still losing stuff. It's decay. -0.7353 grams per day. It's a beautiful little relationship there, right, between the rate and the amount. We can use it in either direction too, right? Like here, we're kind of going from knowing that we had 8 grams to seeing the decay rate. We could do it backwards. If somebody had said, oh, you know what? There was some time, and at that time, the decay rate was -0.7353 grams per day. We could be like, hang on. We could put that in for y prime, divide by k, and find out, oh, that's when you had 8 grams. Then we could work backwards and even figure out, oh, that was at the 12-day mark. But it is such a beautiful tie to know that we can go from amount and then get to rate, or back and forth. And so that's our story there for exponential growth and decay. They're really the same thing. It's just that with decay, you've got a negative up in that exponent. And then next day, we're gonna expand on this a little bit and look at something called Newton's law of cooling, and then all the questions that feel like them.